Okay, students, now we'll say about potential due to a non-conducting uniformly charged sphere. That is, this is a sphere and it is of radius r. It is a non-conducting sphere which is uniformly charged. That means the charge is distributed throughout its volume like this, and we have to calculate the potential due to this uniformly charged non-conducting sphere. For that, let's say we are considering a point which is outside. The point which is outside and the distance from center to this particular point, let's say it is small r. Let small r be the distance from center to this point. Then we can say the potential at a point outside, it will be equal to potential due to a point charge, and as we know potential due to a point charge is kq by r. What is small r? Small r is the distance from center of this sphere to that outside point. Or we could write it as potential at a point outside as 1 by 4 pi epsilon 0 q by small r. This is the expression for potential at a point outside. Then let's go for potential on the surface. Then for saying potential on the surface, let me define a point A. This point is on the surface, and potential on the surface, we have to make a slight modification in this. That is the only modification that we have to use is instead of this small r, we have to substitute capital R. Kq by capital R. What's capital R? Capital R is this distance. Okay, this distance. Then we could write it like this also. V on the surface is 1 by 4 pi epsilon 0 q by capital R. Now we are having potential on the surface also. Then let's find out potential inside the non-conducting uniformly charged sphere. For that, we have to consider a point B. Look here carefully. This is a little bit trickier. This is the point B. The distance from this point B to the center, it is x. Distance from point B to the center of that sphere is x. Now in this case, there is a work required to move a charge from surface to interior point. In the case of a in the case of a conducting sphere or a spherical shell, there was no work required to move a charge from surface to B. But in this case, there is a work required to move a charge from A to B. Therefore, let's find out the potential difference. Let's find out the potential difference between these 2 points. I'll write VB minus VA is the potential difference between these 2 points. Why VB minus VA? It's because VB will be greater than VA. The work done to bring a unit positive charge from B, infinity to B, is greater than the work done to bring a unit positive charge from infinity to A. Okay, so for VB minus VA, we have to calculate it. For calculating it, let's recall some basic expressions. We know electric field intensity is the negative gradient of potential, that is dV by dx. Then from this equation we could write dV is equal to E dx, and from this equation we could write dV is equal to minus E dx, and V is equal to integral of E dx minus. Then we will use this integration. If we are using this integration, we could write VB minus VA, it is equal to integral minus integral of E dx, then from where to where, and the integration is from r to x. We have to integrate it from r to x. Okay, r to x. Then we will substitute for E. What is E? E is the electric field intensity inside a non-conducting uniformly charged sphere, and we have learned electric field intensity inside a uniformly charged non-conducting sphere is kq small r divided by r cube, where small r was this distance. Therefore in this case we could write E is kqx divided by r cube. Then let's substitute for E in this case, and we will get integral r to x minus sine, then instead of E, k q x divided by r cube dx. Taking the constants out, k q capital R cube, they are constant, therefore k q divided by capital R cube is taken out, and if there is a negative sign we could neglect that negative sign and change the limits. That is, I'll write from x to r by changing the limit. Since we are having a negative sign, it is from x dx. What is integral of x dx? It is x square by 2. Therefore kq divided by r cube square bracket x square by 2 within the limit what, r to x. Then substituting upper limit and lower limit, we will get kq divided by r cube into r square by 2 minus what, x square by 2. Then by 2 can also be taken out. It will be kq by 2r cube into r square minus x square. Okay, this is the potential difference. What was this? It is VB minus VA. It was VB minus VA. Let me write it over here. We are getting VB minus VA is equal to kq divided by 2r cube into r square minus x square. Is this the answer? No. This is the potential difference. Then what is VA in this? What is VA? VA is potential at this point. That is, VA is potential at the surface. VA is potential on the surface, and it is KQ by capital R. Okay, therefore I could write VB is equal to VA plus KQ divided by 2R cube into R square minus X square, and we could substitute VA as KQ divided by R plus KQ divided by 2R cube into R square minus X square. Okay, then if I am creating the common term in both, that is, over here it is kq divided by 2r cube. In order to create a term like this, let me say I am multiplying and dividing by a 2. Then if I am multiplying with an r square over here, I could make this r cube. Okay, therefore I am multiplying an r square and dividing an r square and multiplying a 2 and dividing a 2. I could make it like this. Then we could take this kq divided by 2r cube common out. Then we will get kq divided by 2r cube into, over here there will be a 2r square plus r square minus x square. That means 2r square plus r square, it is 3r square. Therefore let me write it over here. That is, we will get potential at the point B is equal to kq divided by 2r cube into 3r square minus x square. Okay, what is potential at the point B? Potential at the point B is potential inside. Therefore, we can write potential inside is equal to kq divided by 2r cube into 3r square minus x square. This is the expression for potential inside a uniformly charged non-conducting sphere. Hope you have understood this. This is an important derivation. Recalling, potential outside is kq divided by small r. Potential on the surface is kq divided by capital R. Potential inside is kq divided by 2r cube into 3r square minus x square. And these all potentials expression can be expressed in terms of volume charge density also. Since we are not having a space over here, we are not expressing it like this. You should remember the formula in terms of volume charge density also. Okay.